Hello everyone. Today we're going to be talking about the fundamental theorem of asset pricing. Now this topic is going to be a bit more complicated than the previous videos I've done, so just bear that in mind when you're watching this video. Now this is the framework we're going to be working with. It's got a bunch of definitions, but they're quite abstract. So to make them a bit more easy to understand, what I'm going to be doing is using the binomial model that I introduced in the previous video to illustrate these definitions in a practical setting. So let's get straight into it. It is going to require some linear algebra, and we're going to be using one functional analysis result further on. As usual, we're going to be working with just two times. The present time, denoted by small t, and the future time, which is denoted by big T. Now, we're going to start by recalling the definition of arbitrage opportunity. I actually never defined it in previous videos. I just used the concept or the intuition. But we do need a very formal definition for what we're going to be doing. So this is the definition. Definition of an arbitrage opportunity is when you have a portfolio whose present value is less than or equal to 0, and in the future it is guaranteed to be greater than or equal to 0 with a positive probability, positive chance of being greater than 0. Just the first line. Or if your portfolio is worth a negative amount now, and it's guaranteed to be worth a non-negative amount in the future. As a definition of arbitrage opportunity. Okay, so let's start with the framework. We're going to be working with n assets, big N assets, from asset 1 all the way to asset big N. Now, in our binomial model, this big N was equal to 2. We had the asset number 1, which was cash, and the asset number 2, which we call the underlying asset, asset S. Now, the second thing we're going to introduce is the spot price vector. This spot price vector is going to contain information about the current price or the spot price of every single asset. The ith entry is going to contain the spot price of asset I, from I equals 1 to I equals big N. And we're also going to want this vector to be a column vector, so we're going to take the transpose of it. In our scenario, unfortunately, from the binomial model, we used some clashing notation. We used ST as the price of this underlying asset S, which is the same notation we're going to be using for this. But just bear that in mind, this ST is using the notation from last time, not from this time. So why is ST in binomial model equal to 1, comma ST? Well, the first asset is cash. What's 1 unit of cash worth? 1. What about the underlying asset, S? The spot price, using the notation from previous video, was ST. So this is our spot price vector. Now, we go on to introduce what different states are. The binomial model, we had only 2 states. 2 states are sort of the ending outcomes at time big T that we can have. We could either have the underlying asset going up to SU or going down to SD. We're going to call the first one state 1 and the second one state 2. Now, what does this matrix D represent? It's going to represent the values of the assets in the future depending on which state we're in. So, the ijth entry is going to be the value of asset I at state j. So what would D look like in our binomial model? Well, recall the cash, if we invest 1 unit, in the future is going to return that 1 unit multiplied by the continuous compound interest. So e to the r t minus t. And that's always going to be the same regardless of the state that we're in. It's independent of the underlying asset. And the underlying asset was either going to be worth SU in state 1 or SD in state 2. Now, if you notice, the columns represent different states, so state 1, state 2, and the rows represent the different assets, asset 1, asset 2. So the value of cash in state 1 is this, the value of cash in state 2 is the same thing, and then the value of the underlying asset in state 1 is SU, and in state 2 it's SD. So this is what D would look like in our scenario. And I'm going to be introducing one last piece of notation before we get onto this, which is going to be theta, which is going to be used to denote our portfolio. So theta is going to go from theta 1 all the way up to theta big N. And this is going to represent the amount of each asset that we're holding. So theta I is going to be amount of asset I that we're holding. Why are we using this notation? Oh, and we're also going to want this to be a column vector. Why is this useful? Well, we can represent the current price of our portfolio at the present time very conveniently just by taking the dot product of our spot price vector with our portfolio. Why? By the way, this transpose, since both are column vectors, this is doing the transpose, so it's a row vector times the column vector, which is just a dot product. Why is this true? Well, this, if we expand it, it's just going to be theta 1 times st1 all the way up to theta big N times stn. This is the amount of asset of asset 1 that we hold in our portfolio, and this is the price of asset 1, the present price, the spot price. And we add all of these together all the way up to the amount of asset N that we have times the spot price of assets N. So this whole thing is going to be what our portfolio is worth at the present time. Now finally, let's address this. This is just going to be notation that we're going to be using for vectors. Rn plus is going to denote the vectors in Rn with every single entry being non-negative, and we're going to denote that by greater than or equal to 0. We're going to denote by x greater than 0 to be all of the vectors that are have every single entry being non-negative and at least one entry is positive. That is those vectors that satisfy this, and then some entry is greater than 0. And finally, we have Rn plus plus, which is going to be all of the entries that have all of the vectors that have every single entry strictly greater than 0. And we're going to denote this by 2 greater than signs. Okay, so now what I'm going to do is get rid of this because it's no longer useful. And I'll just keep this here. I'm going to say theta is our portfolio, and st transpose theta is spot price of our portfolio. And I'm going to rub this out. Okay, I've got a few more things that we need to introduce. We need to introduce, first of all, what d transpose theta represents. And the way we do this is we just expand what this expression would be. Theta, we're going to let, as before, theta 1 all the way up to theta n, big N. What would this be? Well, this would just be d1, well, I'm going to write this, theta 1 times d1, 1 plus dot, 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 plus theta big N times dn1. So that's going to be the first row, and then all the way down to the nth row, which is going to be theta 1 times d1n plus dot, 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 theta big N times d big N small n. So it's going to be an n-dimensional vector, n as in small n dimensional vector, and what each row is going to represent is the value of our portfolio at time big T in the future. Why? Well, as usual, if we just look at the first row, each of these entries have j equal to 1, so we're only dealing with state 1, and it tells us the value of asset I. So this is the amount of asset 1 that we hold times the value of asset 1 at state 1, plus dot, 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 the amount of asset n that we hold times the value of asset n at state 1. So that's the first row, and all the way up to the nth row. Okay, I need a quick break. Sorry, I was getting a bit tired there. Okay, now the last thing that I'm going to do, sorry about all these definitions, is I'm going to replace this with this notation. So this price of our portfolio is now going to be given by this. So I'm going to replace this by saying ST theta is less than or equal to 0. And this thing here, I'm going to replace by S transpose T. And then these things here, this is going to be the same as saying D transpose theta is greater than 0 using this notation. Here we are. This is going to be a vector using this notation. This is the same thing. And this is the same thing as saying dt theta is going to be greater than or equal to 0. Now, I'm not going to explain this in much detail. It's just, if you're a bit confused about this, just pause the video, look at the definitions again, and really understand what each of these are saying. So I'm just going to write this down. I'm going to rub this out. I'm going to write it down. dt theta is more than 0. dt theta. This is supposed to be greater than 0. Greater than or equal to 0. By the way, I didn't mention this. We're going to take each state to be to occur with a positive probability, right? No state is never going to occur, and that's a bit relevant because of this. Okay, now that's pretty much all the base work done. Now, the last thing we need to introduce before we get to the fundamental theorem of asset pricing is the concept of a state price vector, which we're going to denote by psi. Now, psi in Rn++, so every entry is strictly positive, is going to be called a state price vector if our spot price vector is given by d psi, our matrix psi. Now, this is going to be useful later on, but before we get to that, let me just make a claim, because psi at this moment we don't really know what it is, but this claim will make what psi is a bit more clear. I'm going to claim that if we let psi be psi 1 all the way up to psi n, I think it's small n dimensions, then I'm not going to write this down, but I'm going to explain it. I'm going to claim that psi I is the marginal price of increasing the value of our portfolio by 1 in the state number I. And that's a bit confusing, but I'll explain what I mean now. This means that if we have a portfolio theta, and we want to slightly alter it so that our value in the future is the same in every single state except state number I, in which case we want to get 1 more, only if we land in state I, then what's that modification going to cost us in terms of our portfolio? How much more expensive is our portfolio in the present going to be compared to our previous portfolio? If we want to increase that small amount in only state I and keeping every other state the same. So the way we're going to prove this is we're going to be using, as in the previous video, the Arrow-Debreu securities, which we're going to assume exist. We'll touch on that later on. What are these? Well, we're going to assume that there exists portfolios theta I, we're going to denote like this. This isn't the ith entry, this is just a separate portfolio. Such that d theta I is the Kronecker delta. As in, this portfolio is going to return at time big T 0 in every state except in state number I, in which case we're going to get 1. So if we assume there exists such a security, such a portfolio, then this is really what we need. We need to find what the price of this portfolio is. Because if we have already one portfolio, theta, and we add theta I, this is precisely what we need in order to increase our value in state I and keep the rest exactly the same. So we need to find what the price of this is at the present time. We've got a formula for that. So the price of such a portfolio is going to be ST transpose theta I. And now we've got a formula for ST. So if we substitute this formula here, we're going to get psi t dt theta I. But this is just the current code delta. So psi t delta I, which is going to be psi I, which is what we claimed. I didn't write it down, but it's what I said before. So, okay, we've got more or less an intuition of what psi might represent. And now we're going to get into, finally, the fundamental theorem of asset pricing. I'm going to delete this because we're not going to be using it, but I'm going to keep this thing here. Okay, finally, let's state the fundamental theorem of asset pricing. This is going to say that we have no arbitrage opportunities if and only if there exists a state price vector. Now, we're going to find an equivalent formulation of this thing here using the thing we explained before. But actually, we'll do that later on. I'm going to state here in the side the functional analysis theorem I was telling you guys about that we're going to be using to prove this theorem. And that is called the hyperplane separation theorem. This is going to say, it's a bit long. If we have mk, that are subsets of Rn such that mk are closed convex cones with m intersect k equal to 0, just a 0 vector, and k not being a subspace of Rn, then there exists a non-zero functional such that fx is strictly smaller than fy for all x in m, y in k without 0. This is what the theorem says. And we're also going to be using one other linear algebra result, which is quite straightforward to prove, that any linear functional in Rn is of the form the dot product between some constant vector v0 and x. These are the two theorems we're going to be using to prove this theorem over here. Okay, now let's get straight into it. We're going to start by defining m and k to be the following things. Now this is just going to be scalar value, and this is going to be n-dimensional vector, so this is a subspace of Rn plus 1. And then we're going to take k to be Rn plus 1 plus. So the vectors in Rn plus 1 with non-negative entries. Now I mentioned before that this wasn't very useful, so we're going to use an equivalent characterization, which we're going to claim here. No arbitrage if and only if m intersects k equals 0. Well, suppose there's no arbitrage. Then any vector such that minus s small t transpose theta is greater than or equal to 0, and dt theta is greater than or equal to 0, that is the intersection of these, is going to be such that this is more than or equal to 0, But we have no arbitrage opportunity. So this can't happen and this can't happen. So we must have that both of these are equal to 0. Equal to 0 and equal to 0. So the intersection is contained in 0, and it also clearly contains 0 if we just take theta to be the 0 vector. So we've proven one direction, and the opposite is more or less the same thing. If the intersection is 0, then this can't happen, because otherwise, well, this can only happen if these both things are 0. Otherwise, we would have either this or this. Okay, I'm not going to develop that too much because I think it's quite straightforward. Okay, so now we've got to prove just this thing here. I'm going to move this up here. That if M intersects K equals 0, if and only if there's a state price vector. Okay, and now we get into actually proving the theorem. Let's prove this direction first. I'm going to do it over here. I'm going to move this. If and only if there exists a psi. Okay, I'm not going to write the whole formulation, just psi, the state price vector. Okay. Well, we can start using this theorem. We've got M, which we can, and M and K, we can check that both of these are closed convex cones. They've got intersection equal to 0. K is clearly not a subspace of Rn. Actually, we're taking here n to be n plus 1. So maybe let's not do dn, let's do d for example. D, to avoid getting confused. D, 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 and D over here. Okay? These satisfy these conditions, so we know that there exists a non-zero function of f such that f of x is strictly smaller than fy for all x in M and y in K without 0. What we're going to do now is fix a y in K without 0. And we're going to notice that for each x, the following is going to be true. Since x is a subspace, we're going to have that lambda x is going to be in M for all lambda. We fixed x and y, by the way, before. For all lambda in R. So f of lambda x is going to be strictly smaller than f of y, which means that lambda f of x strictly smaller than f of y. But the only way this can be true is if f of x equals 0. Otherwise, this left-hand side would be unbounded, not bounded by f of y. So we deduce that f of x equals 0. But now the x we chose was arbitrary in M, which means that f vanishes in M. Okay? Now, oops, let me delete. Actually, let's keep that for the moment. If we fix such an x, then we know that f of y is greater than 0 for all y in K without 0. And K without 0 is just going to be R plus plus n plus 1. Okay? So, now we're going to use this result here. And I'm going to do this beneath, over here. Let's write f of x as b not transpose x. Actually, let me do this with y. We know that this has to be greater than 0 for all y in here. In particular, we can take y to be the basis vector, so 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, etc. Which is going to give us that every entry in V naught transpose, or V naught, is going to be strictly positive. So we deduce that V naught is in R n plus 1 plus plus. That means every single entry is greater than strictly greater than 0. But now we also know one other thing. We know that f vanishes in M. And if we express f as the following, if instead of taking just this whole vector, we take, say, y1 and y2, where y1 is going to be, y1 is in R, and y2 is in Rn, right? This is n plus 1 dimensional, so we can still take 1 and 2. And let's write this as v0 being alpha and say phi. So this would be alpha y1 plus phi transpose y2. This is a scalar value. Both of these are scalar values. And this is an n-dimensional vector, and this is an n-dimensional vector. But if we now take y1 to be, where is this? This, and y2 to be this thing in the right has to be equal to 0, because f vanishes in M. Theta dt theta equals alpha minus alpha st t theta plus theta transpose d theta theta. Sorry, d transpose theta. And now this has to equal 0 for all theta, because f vanishes in M. So we deduce that minus alpha st t equals phi t dt. If we take transposes of everything and rearrange a bit, sorry, because we're passing on to the other side. This is going to be d1 over alpha phi. But this phi has entries in v0. And we already said before that v0 has every entry strictly greater than 0. And also alpha is greater than 0. Which means that this thing here is going to be a vector with strictly positive entries. So it's going to be our required state price vector, because st is equal to d, and this would be our psi. We would define this to be our psi. Okay, so we've proven one direction. We've proven the hardest direction, by the way. So we've proven this direction. So I'm going to delete this so I have a bit more space to prove the other direction, and then we'll be done for the video. Okay. I'm going to delete this, and I'm going to delete this. Okay, drop that. What's the other direction? Well, the other direction says that if we have a state price vector, then the intersection of M and K has to be 0. Well, let's start by assuming there is such a psi. Suppose there exists such a psi. Now, we want to show that let's write this as want to show that any theta with minus st transpose theta greater than or equal to 0 and dt theta greater than or equal to 0 has to be such that st theta and dt theta are equal to 0. Okay? How are we going to do this? Well, we're just going to substitute the st into here, the formula for st. Suppose that we have a theta with these conditions. dt theta greater than or equal to 0 has to imply that psi transpose d transpose theta is greater than or equal to 0. But we also know, we're assuming that, I meant to write this thing here in the left, minus, and then we've got this smaller than or equal to 0, right? I substituted the value of st here. Sorry, I'm getting super confused right now. There we go. st transpose. Substituted the value of st transpose into here to get the theta. Smaller than or equal to 0. But we also have the condition that dt theta is greater than or equal to 0. That means that every single entry is greater than or equal to 0. But psi t is in Rn++. So the only way this can be true is if dt theta, this whole thing, is the 0 vector. So precisely what we wanted to show. So let me recap what we did here. We want to show that if there exists such an psi, then the intersection of m and k has to be equal to 0. Suppose there exists such a psi. We want to show that if this is true for some theta, then these two things have to be equal to 0. Assume there exists such a theta. Then we derive that this thing in the left implies this thing in the right. And dt theta is greater than or equal to 0. That means every entry is non-negative. But psi is such that each entry is strictly positive, so the dot product can only be less than or equal to 0, in fact equal to 0, if dt theta is equal to 0. That means what we wanted to show basically, that the intersection is equal to 0. And that's the fundamental theorem of faster pricing proved. That was a long video and it is a bit complicated, but it's the only way really to prove this theorem. So I hope you enjoyed this video, and I'll upload a future video where we use this as a result to develop a bit more of the theory. So thank you for watching.